My name is James Shockley. Welcome for coming out. This is scratched in data, the time I leak coded my way through buying a washer and dryer machine. So I am a founding engineer at Norello. This talk is first and foremost and primarily a story. And for that purpose, I hope it is entertaining and educational and scratches that nerd itch for you. There's a second story here. Consider it a little bonus talk for being friends of Barry. As a little treat. It's one that I didn't realize was being told at the time, and it's one that I only realized in retrospect. So I hope you stick around for it. Couple little slides for that at the end. But first and foremost, this is a talk about laundry machines. So let's start with getting dirty there. Okay, cool. So I need to set the scene with a little bit of world building. The year is 2023, it's December. My girlfriend and I had just moved from a tiny for us apartment to a new to us townhome. Me, at the time, I was recovering from a surgery. I was building Norello at the time. We were preparing for this massive 1,000-person hackathon. My free time was zero. Norello. My free time was zero. My tolerance for bull was zero. And my willingness to consume another meal replacement shake was absolute zero. My girlfriend, Emily, absolute angel. In this moment, more the biblically accurate kind, considering the move and having to move everything for me. So as a part of moving into this new to us townhome, we had community laundry, right? It was a short little walk from my apartment. It was about $2 per load, so it was, relatively cheap in the grand scheme of things. So despite having to give up our set, we kind of felt like we had it made. Over the coming weeks, that deal we had with this laundry devil started changing. Firstly, those $2 per load really started adding up, and secondly, one day we pulled out a load and it kind of smelled like pickles. So suffice to say, from this point in the story on, we have a little je ne sais quoi about us. So we knew it would be better and more convenient if we were to buy our own set, but it had to be cheap, it had to be reliable, and most importantly, it had to be delivered since I was completely useless at the time. So I was also, we were preparing for this hackathon, and I was totally gassed with preparing for that. So overall, I was being picky, right? I was holding loose opinions extremely strongly, and I wasn't willing to budge on them. So we broke a few 20s into a change jar, and we made peace with smelling like pickles. For a while, until it became unbearable. So we decided on a date that we would go out and venture into purchasing this new washing set for us. And we settled on a date for that. We said that we would go into this day having done all of our research in the places that we wanted to visit, the inventory that was available there, and lo and behold, we find ourselves on January 28th, the day that we decided to do so, with absolutely zero preparation. So the day begins. We start off the day with no preparation or research, right? And we're just not communicating, not with the stores to call to research inventory, and not with each other to tell each other that we hadn't prepared, right? Because either of those would have been an admission that we had procrastinated. Overall, we're coming to terms with procrastinating, coming to terms that we had procrastinated. So after about 45 minutes of getting absolutely nowhere, nor defining where our end goal would be, we decided to just start calling stores, right? Make some moves. So we called one, a local appliance retailer, who happened to put out something that was perfect for us. It was cheap, it was reliable, it was just scratched, and they were putting it out in 5 minutes. So we were there. We were the first people in front of this machine, and I didn't know what to do. I'm like looking at this thing, I'm like playing with the lid, I'm like, yeah, this kind of looks like a washing machine, but I have no idea what to look for, right? And that's when it happens. That's when somebody comes up, and they take the tag off it, and they go to the register, and they check out, and there was absolutely nothing I can do. The universe manifested, hand-delivered a W to me, and I still fumbled the bag, right? So we leave, hats in our hands, absolutely devastated. And I mean, to this day, I've still never seen a deal like that before. But we had learned that we needed to get serious. We needed to level up. Our humble Google spreadsheets needed an upgrade. So we get back home, the plan is such. I would run dispatch, because again, useless. And my girlfriend would run out to all these stores doing research for us, doing what we intended to do going into this day, right? So to recap, there's a traveling woman going on sales, and we want to optimize for the number of locations that she can visit. Is this starting to sound like a familiar problem to anyone? Okay, I see a couple of people nodding. Yes, if this sounds like a traveling salesman problem variant, it is. So the TSP likely needs no introduction, but let's do one anyways. So say, oh, this is what I was feeling like internally when somebody bought that washing machine out from under us. So yes, the TSP. So let's say hypothetically you want to visit every instance of a major household corporation, corporate juggernaut in the commercial retailer space, right? So you want to go to every Radio Shack in the US. And you want to start in the metropolis of, and so you want to go to all of these locations, right? But you're tight on time, you're tight on gas money, so you want to make your trip as optimal as possible, right? You want to spend as least amount of time on the road and as much time in shacks as you can, right? So this is like the word problem form of the traveling salesman problem, right? There's a bunch of different ways you can get to all of these shacks, but there's one optimal route that requires the least amount of time on the road for you. So let's take this word problem and move it into a problem definition, right? Because we need to mutate it a bit. So we're going to have two shacks here, Shack A and Shack B, and I've asterisked Shack B just to indicate that we're going to start there. So these are going to be nodes on our graph. We're going to be talking about a graph problem. This should be our first tip. These graphs are going to have edges between them, or the roads that will connect them, right? A common assumption when talking about the TSP, especially in academics, is that you also make a third assumption, right? You're going to make the symmetric assumption, and that your edge X is going to equal your edge Y. So you're going to have a symmetric graph. Now you're also going to assume a complete graph, right? So let's throw a wild card in. Let's throw in a third shack, right? So now you're going to have all of these different tours, right? All of these possible ways that you could commute between your various shacks, right? You're going to have all of these tours, but there's only one that you want to choose. So this tips us off that it's an optimization problem. So it's extremely clear that this is the tour that we're going to choose, right? Since it's the shortest one. Now we're going to make some assumptions here to mutate this into our problem definition, right? So these shacks, they close at specific times, right? You can't go to a shack to research their inventory if it is already closed by the time you arrive there. So we're going to associate a closing time with all of our nodes. Now, assuming again a complete and symmetric graph with edge weights of 30, there's only one way that we can optimize for the number of locations we visit, because if we go from Shack B to Shack C right here, and then Shack A, we can visit all three. But assuming that same 30-minute drive time, if we go from Shack B to Shack A, Shack C will be closed by the time we arrive at it. So there's a way that we need to optimize for our number of locations that's different than optimizing for the distance that we're traveling here. So the basic approach that we're going to take here is we're going to use a heuristic. So let's talk about heuristics for a moment, right? So if we go to Shack C first, we can do that. So our heuristic approach will be, if we can visit, of all the locations that we can make it to before they close, we're going to travel to the one that closes the earliest. It's very simple, right? And this is a heuristic. There are cases in which this approach performs suboptimally, right? And a heuristic, simply put, is any approach to problem solving that's not perfect, but good enough. And there's a third part after this, which is that usually good enough is perfect, actually. Because engineering is all about trade-offs. And sometimes times to completion is a trade-off that's willing to be acceptable to make, right? It's important to know that your derivative is a valuable tool for understanding the instantaneous rate of change or sensitivity to a rate of change of your request rate, and can be used as a custom metric used in scaling factors, right? It's way more important to know that it's way easier to take the queue depth of your request queue in order to do auto scaling. And even more importantly than those things is it's way more important to know when you're scaling for a 1,000-person hackathon and it's $100 to over provision your infrastructure for the weekend, it's way easier to spend $100 to over provision for the infrastructure rather than dealing with the opportunity cost of either of those first two things going wrong during your hackathon. It's a heuristic. It's a good enough but perfect approach to solving your problems, right? A heuristic is not an excuse to write crappy code. Don't submit a PR and tag me like this and say it's heuristic. Okay, so our solution to this problem roughly falls into like the greedy modified nearest neighbor classification of a solution to it. So what does that look like? I don't know. I asked Midjourney to visualize it for us, so hopefully we're all on the same page here. Okay, awesome. So here's what it roughly looks like in a diagram. So we will travel to C because it is the location that we can make it to that closes the earliest, and we will take our time that we're starting out with, we will increment our start time by the drive time, which would be 20 minutes in this case. So now our time, if it starts at 12 o'clock, our time when we arrive at C would be 12:20, and we would associate like an extra 15 minutes to call to visit the inventory. So that's how we're keeping track of time, right, to make sure that we're arriving at these locations before they close. So, great, we've got our problem solution. We know roughly how we would solve this problem in an abstract sense. Now we need the data for it, right? So how do you go about getting the data for your nodes and your edge weights? So I'm going to use the absolute goated stack that I love to solve business problems with. It's called the GSP stack. It's Google Sheets and Pandas, and it needs more recognition in this space. I feel strongly about that. So what we're going to start here is we're going to start with the using Google's Maps API in order to find a list of all of the used scratch and dent appliance resellers within like 40 miles of me or something, or whatever it was. So by default, this is going to give us our list of businesses as well as their Google Place IDs. So these are the basis for what's going to become our nodes, right? But the Google Maps API will only tell you whether a location is open at that very moment. So in order to find the store closing times, we need to pop over to the Google Places API, use that Google Place ID from the Maps API, and then join in a structure that has the operating hours and flatten that nested structure, right? So we merge that in with our data frame, and we represent that in a columnar format in this Excel workbook. The other huge benefit of the GSP stack is you can work with like non-engineers, like for example, I can work with my girlfriend on this, and it's just a simple Excel workbook, right? So we can import back in her changes by reading that workbook. Okay, cool. So how do we get the edge weights, right? Because now we've got our nodes. We know the businesses that we want to go to, and we know their closing times. So how do we get our edges? Well, the naive approach, the approach that I started with, was just taking each location and finding the distance relative to each other location using that same Google Distance API, which is excellent. It's what I started out with. But when I was in the documentation, I noticed the Google Distance Matrix API, which the business case here is, say you're like an ambulance dispatcher, right? And you've got buku ambulances and somebody's got a boo-boo, and you need to find the nearest ambulance to dispatch to them, right? So you can use the Google Distance Matrix API to provide a list of locations or sources and a list of destinations. And you will return from that a matrix of the distances, right? Clever naming. So there's a couple of limitations with this inherently because the complexity can absolutely balloon, as you can imagine. So there's a limitation of 25 origins and 25 destinations, which at this point we had about 40 stores in our data frame, right? So no bueno. So what I did was I assumed that I pared down our data set to remove all of the locations which were already closed for the day because, who cares? And I removed all of the locations that were open Sunday because we can just visit those tomorrow, right? We're just trying to save the most that we can of this single day. So that brought us down to 21. Awesome. So we have a 21 by 21 matrix, 21 origins and 21 destinations that we need to find the distance for. And that's when I got back an error. Hey, too many elements that you're requesting that we return from us. That's when I learned there's a limit on 100 elements that can be returned from the Google Distance Matrix API. So, okay, we're back to the drawing board. Not really though. What we can do is we can approach this in a stepwise fashion. So we can take one of our origins, right? And we can project that over all 21 of our destinations, which would give us 21 elements in our return list, right? So we iterate over all of our origins and we find the distance to all of our destinations. And then we do that for the next origin, right? The same thing. And then what we end up with is a list of 21 of these files that we save the responses for that have all of our destinations in there for one origin and a little below there you have the distances between all of them. Okay, awesome. So now we have all of our nodes, their closing time, and their distances, right? So we can construct the problem here in real life and send Bay on the way optimally. So let's look at the code for that. I'm skipping over the boring file and network manipulation stuff because like whatever. Okay, so we're gonna start off with a list of unvisited stores, or a set specifically. So this is, again, at the start, it's going to be 21 because we've got 21 stores that we haven't visited that are still open, okay? So now that we do this, we need to find the first store to start at. So again, just starting with heuristics, naive assumption here, I know that I can make it to any of these stores in 45 minutes, so we're just gonna assume that as a blank rate rather than finding the distance from my house to all of these stores. Also, don't dox me. So we're gonna choose the first store. We're just gonna iterate all of them. We're gonna find the one that starts earliest. And we're going to say, like, whichever store closes first, we're gonna head to that one first, and we're going to set that as our current store. What we're going to do throughout this entire process is we're gonna construct a list of paths, or a path, which is a list of our location IDs that we visit in order. And what we're going to do as well is we're going to increment our start time by the travel time as well as the time we're spending at our store, which in this case, I'm making that flat assumption of 45 minutes to get to any of our first store, right? So here's where we start constructing our path, and then we remove that store from our list of unvisited stores because we consider it unvisited, right? And this is just a little utility dictionary for finding our stores, right? That we'll use later. So while we have stores that are yet to be visited, we're going to consider all of the candidates, right? So our candidates are going to be any of the stores that we can make it to that haven't closed yet. So we're going to look at our arrival time, which is our current time plus the edge weight of that store, right? So if we're going from A to B, how long is it gonna take us to go from A to B? We add that to our current time, and then we see if that's less than the closing time, right? If we can make it there with a 15-minute buffer before it closes, then we're going to find that time delta, and we're going to push that onto a priority queue. And after we've constructed this priority queue for all of our stores, then we're going to pop from it, right? So this is gonna get us to the store that closes the earliest, right? And then we're going to increment our current time by that edge weight to get to that store and add 15 minutes to go and browse the inventory there, right? So we're gonna add that, we're gonna make that store our current store, we're going to append that to our path, and we're gonna remove that from our unvisited store. And after this, what we end up with is a list of 8 stores, which is more than a third of what the stores that we could visit. When they were starting to close in 2 hours, this is actually pretty good to salvage some of our day, right? So we end the day absolutely exhausted. But we had done what we should have done previously, so we felt some accomplishment from this. But this is not where the story ends as well. We still need to buy a washing machine. So how do we do that? So I knew at this point in the story that we weren't gonna get what we needed to do this weekend, and I could act on a deal if I found one during the week. I could take some time off of work in the morning to execute, but I couldn't spend all day like looking at websites for inventory, right? That's boring, and we know how to automate these things, which comes to the topic du jour lately, which is LLMs of coding. So my personal perspective on whether or not to use LLMs for coding is a popular business maxim, right? If it's not a core competency, outsource it. So effectively, I'm asking myself the question, is learning a web scraping library going to advance myself, deepen my knowledge as an engineer, or be valuable and a competitive advantage to me in the knowledge marketplace? The answer was a resounding no to me, so I'm going to outsource this to our little robot friend. And I'm going to say, write me a little recursive site scraper that's going to take a list of URLs that we have from our existing data frame, and I'm going to say, write me a recursive site parser that's going to look for URLs that have like washing, washer, dryer. As I found, this included dishwashers, but whatever, we can parse those out later. So my girlfriend and I get a list of all of the locations that have potentially their inventory posted online. We just acknowledge whether or not we review these manually, and now we have a list of all of the websites that have their location and inventory posted online, which is awesome, because now we can write an inventory scraper. So again, I'm gonna go over to our robot friend. I'm using Find and Claude. I really like Find. So I tell it, write me a little Python scraper that's going to return to me a tuple of the price, of the inventory on this page, as well as a link to the inventory listing as well. And I find that providing a clean interface like a list of tuples is far more conducive to getting good results from these things, because I can just take that list of tuples and plug it into whatever storage backend that I need to use for it, right? So providing clean interfaces is something that I found to be remarkably successful with prompting LLMs. Don't give it your entire code base, just give it a clean interface for inputs and outputs, right? So I just copy in the HTML from the developer tools. This is using like a WooCommerce store. I can tell from the CSS or the selectors. So yeah, anyways, I give it the inner HTML for the listings, and it gives me something that's actually really good. So I didn't have to write a scraper, right? And this actually worked right out of the box. So I'm able to now, I now have a script that I can run, one of them for each of the inventory sites that we want to keep an eye on, and we're able to save off and store the inventory and run it every morning in order to update it. So fast forward a couple days and the results start coming in and we start hitting the streets, right? And this is where I want to talk about some of the fun things that I found during this experience of finding a washer and dryer in South Carolina. So here is one of the first websites, and when I went to go copy the inner HTML for this specific website, I was blown away, and I want to take you guys on this journey with me. So this is the website landing page, and it is absolutely goated in my opinion. So I blocked out some of the content on this website, A, because it's identifiable to the business, or B, because Godwin's law has been triggered. And so I also just need you guys to understand that I've also lorem ipsum-fied it as well, for that same specific reason. I need you guys to know that this overfill is not because of my ipsum generator. This was just there in the style. So this is a specific thing that this individual is going for. So anyways, back to the inventory list, which peak design. So I end up finding a washer and dryer set that I can go out for that is within our budget, right? It's delivered, it's awesome, let's go get it. So I call them up, we agree on a price over the phone, I'm out there, I've got my check in my hand, and I'm excited. Actually during the call, it was funny because completely unprompted, they celebrated the great American tradition of having a complicated relationship with the IRS, which strangely was a recurring theme within trying to buy a washer and dryer. Just people would admit to these things, it was wild. Okay, so anyways, back to the story. So we have a price for this washer and dryer machine, and I'm out there, I've got the check already inked, and I'm ready to deal with this man of class, and I get out there and he upped the price. And that was no-brainer for me, I'm out. So yeah, that was pretty scummy. But I didn't leave empty-handed actually. He did give me this, right? And this is probably the part where you think that I'm going to show you some of the pictures from this little comic book, but I've actually been showing them to you this entire time through the slides. So it's pretty high quality, it's awesome. But yeah, so this was just one of the stores. Here's another one which we almost bought from them just from the name recognition alone. Whoever is doing their social media campaign work deserves 2 consecutive promotions, I think, because we almost bought from them just from that mascot. And I mean, just look at this marketing campaign. Just absolute classic, man, banger. Okay, cool. So there was another guy that I call him up and I'm like, hey, what's up? Yo, it's James again. And I ask if it's his business from the Google Place business name that's associated with it. And immediately on the other end, I can hear the vitriol, I can hear him foaming at the mouth. I'm about to call an ambulance for him, but he's pissed, right? He's pissed. And the reason why is because he had a former business partner who tried to do an SEO campaign with him under that phone number, but for a different company name. So now his business is associated with his former business partner who burned him, who did a bad SEO campaign, which I guess my little lesson there is if you're ever in the SEO or client-facing space, never ever burn your customers, because the first thing that your business, that you're gonna be reminded of whenever a customer calls you is that shoddy person's work, and that's gonna be the first and only thing that they wanna talk about. So just don't burn your customers in the SEO space ever. So anyways, we end up finding the perfect 2008 direct drive Whirlpool model, which is an absolute rarity. It's peak engineering, and we've been extremely satisfied with that. So there is a happy story here about being able to leak code your way through buying a washing machine. And this is where we get to the bonus talk portion of this, because I didn't know this story was being told as it was happening. I was just trying to buy a washing machine, right? And now, as I was writing this story down and reflecting on it, I got a little philosophical over it, because I found the leak code in life, right? This was something that I missed entirely during my education. Data structures and algorithms was just a hard thing that I was not talented or good at. And leak code was something that I grinded when I was unhappy at a job and I wanted to jump to another one. It was an obstacle, right? It wasn't a challenge, it wasn't an opportunity to improve my skills. It was something that I had to do and was deeply unpleasant. And somewhere along the way, I just detested leak code so much that I just started doing it 20 minutes every single day. And I detested those 20 minutes. But over time, I started falling in love with the fact that I was getting good at something that I didn't like. I learned to start loving the process. And that's something that's carried on into so many other parts of my career. And I don't even know how it happened. I don't even know why. Like, I started doing it for 20 minutes every single day. But it's something that's paid dividends for me. And nobody has ever asked me to solve 847 shortest path visiting all nodes. But on that day, when I bought that washing machine, I solved this problem, right? So I don't do leak code because I love it, and I don't practice data structures and algorithms because I love it. I don't find inherent joy in orchestrating Kubernetes clusters. Async Rust absolutely broke me when I was learning it. But despite not loving these things, I love the real problems, the real products, and the real relationships that this continual process of improvement and encouragement allows us to pursue. So that's it.